I'm not driving, but I'm going to press this horn and listen the sound. Now I'm driving 40 miles per hour and I'm going to press the horn. So no matter how fast I'm driving, the sound is exactly the same. But this is not true for a person standing by the road when I pressed the horn. The person will listen a shift sound. One great example of this is when a fire truck is passing by you. This sound shift that you listen is caused by the change of pitches before and after the fire truck passes by you. This relationship between the shift of pitch was explained by the Austrian physicist Christian Doppler. In this lesson, you learn the theory behind the sound shift and you calculate the frequencies using the Doppler Effect Formula.
Water and sound waves are mechanical waves. Both need particles in the medium to propagate the energy. We can visualize water waves by observing its ripples and measuring wavelength and period, but it doesn't work the same for sound waves. We can listen sound and sometimes feel its vibrations, but we cannot see how it propagates. However, we can use the water ripples that we can see and apply the same concept for sound waves to visualize and understand its motion. Let's look at this stationary duck. It makes equally distant circular water ripples. But moving duck, the front ripples are closer together and behind ripples are getting farther apart. This diagram represents a stationary duck on a lake with equally circular ripples. This diagram represents a moving duck on a lake with front ripples closer to each other than the back ripples. Remember, the distance between crests of ripples is the wavelength, and the number of wavelengths per second is the frequency. So we can conclude that a stationary duck will produce equally frequencies, and a moving duck will produce different frequencies depending on the direction of its motion. Sound waves behave the same way as water waves do. Let us see how it works. This is a stationary sound source produced by a siren. The siren produces sound waves moving equally to all directions. These blue circles are the crests, and the distance between crests are the wavelengths. Now, if I place two observers on each side of the sound waves, they are going to listen the same pitch. So this is the sound source, and this is the observer. This is for a stationary sound source. Now let us consider a moving sound source, like a police and ambulance or fire truck sirens. The front waves are closer than the back waves. We can see the wavelength at the front is smaller than the back. We know that for the same speed, frequency is inversely proportional to the wavelength. So the front waves have higher frequency than the back waves, which has lower frequency. So at the front, we're going to have a higher, louder pitch, and the back a lower pitch. Likewise, if the sound source is moving to the left, the front left waves are closer than the back waves. So the front waves have a higher frequency and the back waves have a lower frequency. Now when a siren of a fire truck approaches the observer, the pitch sounds higher than the normal because the sound waves crests get closer to each other, causing higher frequency. When a fire truck passes and move away, the observer hears a drop in pitch because the wave crests are spread out and the frequency is lower. The observer perceives the frequency as pitch, and the sudden change of pitch is heard as wee on, wee on. When an observer and a sound source move toward each other, the wave speed and the frequency appear to be higher. So now both the sound source and the observer are moving. Likewise, when an observer moves away from the sound source, the wave speed and the frequency appear to be lower. The Austrian physicist and mathematician Christian Doppler observed the frequency of a wave depends on the relative speed of the source and the observer. The shift of frequency caused by the relative motion of either the source or the observer is defined as the Doppler effect. In 1842, Christian Doppler proposed a formula with frequencies and speed of a sound source and an observer. This is the formula, and let's look at the terms. F sub observed means the frequency received by the listener or observer. F sub emitted means the frequency emitted by the sound source. The V by itself is the speed of sound in the air, water, or liquid. Air, water, and solid. The speed of the observer is positive when the observer is moving toward the source, and is negative when the observer is moving away from the source. The speed of source is negative when the source is moving toward the observer, and is positive when the source is moving away from the observer. So let's do some practice problems using the Doppler Effect Formula. Example 1. What frequency is received by a person standing by the road when an ambulance passes by with a speed of 30 meters per second and emitting a sound from its siren with a steady frequency of 800 Hz? Use the speed of sound in the air, 343 meters per second. So here is the observer when it's stationary, so the speed is 0. And the problem is asking to calculate the frequency observed. So this is the data table. The speed of source is negative because the source is moving toward the observer. Let's bring the table here so we can see better. The speed of the observer is 0, so we don't have to worry about positive or negative. The frequency emitted is 800 Hz and is asking to calculate the frequency observed. So use the formula, the Doppler Effect Formula, and let's do our substitution. So the frequency observed is equal to the frequency emitted, which is 800. And now for the fraction, you just need to do the substitution. The V is the speed of sound in the air, which is 343. and the speed of the observer is 0, and the speed of the source is negative 30. So you do the substitution with the signs, solve the fraction, and multiply by 800. So the result is 877 Hertz, which is higher. The frequency is higher than the frequency emitted by the sound source, in this case a siren. Example, that's the second example, but here is 3. 2 eagles, A and B, fly directly toward one another. Eagle A is flying at 15 meters per second, and Eagle B is flying at 20 meters per second. Eagle A screeches, emitting a sound frequency of 3,200 Hertz. What frequency does Eagle B receive? Okay, so let's set up our table. So the speed of the source, which is Eagle A, is 15 meters per second. It's negative because it's moving toward the observer. The speed of the observer is 20 meters per second and is positive because it's moving toward the source. The frequency emitted is 3,200 Hertz, and we need to calculate the frequency observed. So again, the formula, we do our substitution, 343 speed of sound in the air. Now is plus 20, and on the denominator is negative 15. Solve the fraction, multiply by the frequency emitted, and the frequency observed by the Eagle B is 3,541 Hertz. To finish this lesson, I just want to give you an additional information about Doppler effect. We hear the weather referring to the Doppler radar, which applies the same principle as sound, but instead uses microwaves. The Doppler radar is an application to predict the weather by sending out microwave signals in a circular pattern. Microwaves can travel longer distances. So once the signal hits a raindrop or a denser cloud, it bounces back to the radar. The radar is able to calculate the precipitation distance and speed of the upcoming weather changes. So it's the same principle, but instead of using sound waves, using microwaves. So that's all for Doppler effect.